So the first example is a digital differentiator. Okay. So for a differentiator, we hope that the frequency response of a continuous time differentiating filter to take on this form. Okay. So this is, right, in continuous time, this is a differentiating filter, the frequency response of a differentiating filter. Okay. Right. So if you plot this out, assuming that it's band limited to omega c, then the magnitude, which is the absolute of omega, is just this function here, and the phase is either pi over 2 or minus pi over 2 in the positive and negative axis. Okay. Now suppose that you want to perform this. You want to obtain this effective filtering effect in discrete time using a discrete time filter HD. Now, what would this HD look like? Right. So suppose you sample at a sampling frequency that is equal to 2 times omega c, right? 2 times the bandwidth omega c. Okay. So suppose you sample at sampling frequency omega s, then by what we just derived, we know that we should choose a discrete time filter HD that is equal to a scaled version of HC, right? We know that we should choose a discrete time filter that is a scaled version of the continuous time filter by this capital T. Okay? So if you just substitute omega over capital T inside here, this is what you get. Okay? And the range will then go from, become from omega c to pi. Okay? Okay. Right. So if you want to, double check this, right, you just take this omega equal to capital omega over t, substitute it inside. Okay. So if you want to check, okay, you need this to be less than omega c. Right? If you plug this inside here. All right. Now, what is T? T is 2 pi over the sampling frequency. Okay? And omega s is 2 omega c. So this is just pi over omega c. So if you substitute this inside here, right? Okay, if you substitute this inside here, right, omega c cancels out, and you bring a pi to the other side, and this is what you get. Okay. Okay. So again, if you want to construct an equivalent continuous time filter using a discrete time operation, then you should choose a discrete time filter that is equal to a scaled version of this continuous time filter over the band limited range. Okay, and this is what you get for the differentiating system. Okay. All right. Now, looking at this example, suppose we consider a input signal xc of t that is equal to this sinc function. Okay, so a sinc function has a Fourier transform that is this perfect rectangle in the frequency domain, and the output of a differentiating filter is this y sub c of t that is equal to the derivative of the input. So if you plug this inside here, the derivative gives you this. All right? Okay. Now suppose we want to implement this kind of operation in discrete time. Okay. So with discrete time implementation, we first construct this discrete time sequence xdn, which is equal to the sample of the continuous time signal at integer multiples of capital T. Now, if you look at this, this is a sinc function. Okay, this is sinc function with a peak at the origin, but zeros at integer multiples of capital T. Okay. All right. So if you sample this function, you're sampling at 0, t, 2t, 3t, and so on, minus t, minus 2t, and so on. Okay. So the discrete time sequence that you get actually is only non-zero. Is only non-zero at n equal to 0 and 0 everywhere else. So that's basically a discrete time impulse function. Okay. So this is this 1 over t times a discrete time impulse function. Right. The 1 over t is because of this value 1 over t on top. Okay. Now, similarly, the discrete time of the corresponding output signal similarly, if you look at the discrete time version of the continuous time output, right, which is equal to the values of the continuous time output at integer multiples of capital T. Okay. All right. So if you substitute this inside here, okay. So if you substitute nt inside here, right, you will see that you get integer multiples of pi inside cosine. Okay. So for integer multiples of pi, right, cosine n pi is either 1 or minus 1, right, depending on whether n is even or odd. Okay. Now, if you substitute nt inside here, then right, this again is something like a sinc function that is only, non-zero at the origin. Okay. So if you substitute this inside, right, these two terms will cancel out when n is equal to 0. But when n is not equal to 0, the second term is 0, and you have only the first term. So eventually, what you get is just minus 1 over to the power n over nt squared, n not equal to 0, and 0 for n equals to 0. Okay? Now, what's interesting is that here we have a discrete time signal that is just a scale of an impulse. And we have the corresponding output that is equal to this. Okay? So if you multiply both of this by capital T, then what you get is actually the impulse response, right? What you get is actually the response to a impulse function, right? And that is the definition of an impulse response, okay? So the impulse response HDN here is just, T times YDN, which is minus 1 to the power n, and T for n not equal to 0, and 0 for n equal to 0. Right. So from this study, we coincidentally find the discrete time impulse response. Right? We find the time domain impulse response corresponding to this discrete time differentiating filter. Okay. So this is the time domain response corresponding to this discrete time filter. All right. Okay. All right. So this is saying that if you want to have an overall system that is equal to a differentiating filter, then you can, do this by choosing a discrete time filter that has a impulse response equal to this. Okay? All right. Now let's look at another example. Okay. This other example is the half sample delay, or any delay actually. Okay? So suppose you consider a time-shifted system where the output is equal to input shifted by time capital delta. Okay? So if you take the Fourier transform of this, this output spectrum is equal to the input spectrum times e to the minus j omega capital delta. So this is saying that the band-limited frequency response is equal to e to the minus j omega delta, right, over this band-limited region. Okay? Now, suppose you take a sample at 2 times the bandwidth omega c, then the discrete time frequency response HD will be equal to a scaled version of this continuous time spectrum, right? So this is this thing with omega replaced with capital omega over capital T, and the range is again going from omega c to plus or minus pi. Okay? So suppose that this is, the original spectrum of the continuous time filter. Then when you convert it to discrete time, you need to choose a discrete time filter that has a constant magnitude and a phase, a linear phase within each period of 2 pi. Okay? So when you convert the continuous time, so one thing to note here is that when you convert the signal to discrete time, right? When you convert the signal to discrete time, you're taking samples of the continuous time signal at integer multiples of capital T. Okay? Now, if delta is also an integer multiple of capital T, then the time-shifted version, right? Time-shifted version, okay, the sampling of the time-shifted version will just be the shifted version of the discrete time sequence, okay? But if delta is not an integer multiple of capital T, then this ydn will not be simply a time-shifted version of xdn, but instead it will be a resampling of a time-shifted version of the continuous time signal by, capital delta. Okay? So this is just something to take note, right? You have to be aware that even though we're looking at a time-shifted version of the continuous time signal, but when you take the sampling, right, to look at the discrete time signal, the discrete time signal is not simply a time-shifted version of the discrete time version of the input, okay? If delta is not an integer multiple of capital T, then ydn will not be a time-shifted version of xdn, right? Because you're not shifting by an integer number of samples, okay? But instead, it would be a resampling of a time-shifted version of the continuous time input, all right? Okay. Now we can look at a similar example. Now suppose we again consider a continuous time input that is equal to this sinc function. Right? We plug this into this system here. Okay. All right. Now if you take the discrete time implementation, you will get a discrete time sequence xdn that is equal to xc sampled at integer multiples of capital T, which is 1 over T delta n. And the discrete time sequence at the output is the sample of the continuous time output at integer multiples of capital T, which is a sampling of the time-shifted version of xc. Okay? Now, assuming that delta is equal to T over 2 here, then if you substitute xct inside here, you will get sine of pi n minus 1/2 over T pi n minus 1/2. Okay. So interestingly, similar to before, you can see that the input here in discrete time is simply a scale of an impulse function. Okay. So the output that you get, right, should also be a scale of the impulse response. So if I multiply both of these by capital T, I would get a impulse function at the input, and the output will be the impulse response. Okay. So hence, HDN is sine pi n minus 1/2 over pi n minus 1/2. Okay. So this is the impulse response of the half sample delay system. Okay. Okay. So through these couple of examples, you can actually see that we have a convenient way of finding the discrete time impulse response to a corresponding continuous time system that we desire. Okay? So suppose that you know what is the continuous time input-output relation that you want. Then to get the discrete time impulse response, right, that helps us achieve that, you can simply plug in an input that is equal to a sinc function, and then by taking the sampling of the corresponding output, you can get the corresponding impulse response of the discrete time system. Okay? So we mark here. So using xct equal to this sinc function, helps us find the impulse response of the equivalent discrete time filter. Okay. Okay. Right, so up to this point, we have talked about how to perform sampling on a continuous time signal to obtain a discrete time sequence, right, that helps us, perform certain operations more efficiently. Okay? Right. Now, we not only can perform sampling on continuous time signals, we can actually perform sampling on discrete time signals as well. Okay? So we do this following almost exactly the same approach. Okay? So suppose now you want to perform sampling on discrete time signals. Okay? So suppose that xn is our original signal. Then, right, to sample xn, right, we can also multiply it by this impulse train Pn to get a impulse train sampling signal xPn. Okay. So Pn here is this impulse train separated by integer multiple of capital N, which is our sampling period. Okay? So originally, this is a discrete time sequence, right? We have a sample at every integer value of n. But instead, suppose we just want to extract out the value at every integer multiple of capital N. Okay, so we do this by multiplying xn by this impulse train separated by integer multiple of capital N. And this gives us x of p of n that is equal to xn if n is an integer multiple of capital N and 0 otherwise. Okay? So it looks something like this, right? So suppose this is the original xn. If you multiply it with this impulse train, you get only the value of this xn at integer multiples of capital N, which is 3 in this case. Okay? So here, n is equal to 3. Okay. All right. Now let's see what this looks like in the frequency domain. Okay. So when you multiply two signals in the time domain, in the frequency domain, it would be the convolution of their respective spectrum. Okay. So the Fourier transform of this impulse train sampling signal, xp, is equal to the convolution of the original spectrum, the spectrum of the original signal, and the Fourier transform of the impulse train. So an impulse train in time gives you a Fourier transform that is also an impulse train in frequency, separated by omega s, which is 2 pi over capital N. Right, this is the sampling frequency. Okay. Now just have so this is the same as in discrete time. The only difference is that we need to be careful with this periodic convolution, a convolution over only 2 pi. Okay. All right, so we learned before how to, more simply compute this periodic convolution. So the key is that, to take a periodic convolution, right, more efficiently, we can basically take the, convolution from minus infinity to infinity, but taking only one period of one of these signals, right, either a period of p or a period of x. Okay? So suppose we take a period of p, right, a range of p over a 2 pi range, the value of p over a 2 pi range. So this will give us 1 over 2 pi integral minus infinity to infinity p hat e to the j theta times x e to the j omega minus theta d theta. Okay. Now p hat is p over only a 2 pi range. Okay. Now you can see that p is a bunch of delta functions separated by 2 pi over capital N. So if you look only over a 2 pi range, you will actually have only capital N of these impulses. Okay. So you can take any 2 pi range. Suppose we take, from 0 to 2 pi. So in that case, this is just 2 pi over capital N summation k from 0 to n minus 1 delta of omega minus k omega s. Okay? So we take only one period of p to get this, right? To get this p hat, which is p over a 2 pi range, okay? And here we have actually capital N impulses. And when we convolve with this x, it basically moves x to the position of each one of these impulses, okay? So we move x to each one of these impulses. But you have to be careful because x here is by itself periodic, right? Because x is the Fourier transform of a discrete time sequence. So a discrete time sequence is always periodic with period 2 pi. Okay? So this is periodic with period 2 pi. Okay? But nonetheless, when you take the convolution of these two, you get 1 over n summation k from 0 to n minus 1 the spectrum e to the j omega minus k omega s. You have this spectrum repeated every integer multiple of omega s. Okay? Okay. Now let's see what this looks like. Okay. So suppose that this is the original spectrum x. Right? So you can see here that for discrete time sequences, the Fourier transform is periodic with period 2 pi. Okay? And the impulse train signal has a Fourier transform that is also an impulse train separated by integer multiples of omega s. Okay. Now to take the periodic convolution, we take p hat that is p only over a 2 pi range. So if you take this only over a 2 pi range, you get only these 3 impulses. Okay. So you get these 3, which is p hat e to the j omega. Okay? And here, n is equal to 3, right? You have n equals 3 impulses. Okay. All right. So you take the convolution between x and p hat, which will move this entire spectrum, right? Move this entire spectrum to this position, and this position. Okay? So when you move this to this position, right, you also have this moved here and this moved here, right? When you move this to this position, you also have this moved here and this moved here, okay? When you move this to this position, you have this moved here and this moved 2 samples down, okay? Two integer multiples of omega s, right? So eventually you get xp that is like this. Right. So if you move x to this position, you get these, replicas. Right. If you move it to this position, you get these replicas. And if you move it to this position, you get these replicas. Okay? All right. So this example above is the case when omega s is greater than 2 times omega m. Okay? So that there is clear separation between adjacent replicas of the spectrum. Okay? So if that is the case, then you can actually get back the original signal